Okay, good afternoon, everybody. Let's get started. So welcome to 6004. Today we're going to dive into Boolean algebra and logic synthesis. So if you remember from last lecture, we spent most of the lecture talking about the digital abstraction and deriving a signal specification that essentially let us build robust digital systems that then we can connect very easily as long as they follow the same signal specification. And then we started our description or an introduction to combinational devices, which we said are the basic or one of the basic building blocks of digital logic and basically the simplest type of digital device. So today we're going to continue looking at different aspects of combinational devices. And by the end of this lecture, you should be able to essentially go all the way from the functional description of a simple combinational device down to its implementation using basic components. So let's see how this works. Basically, the first part of the lecture we're going to look at Boolean algebra, which is how we precisely specify the function of the device, and then we'll see how to turn that precise specification into gates, into basic combinational logic components. Okay, so as a reminder, a combinational device has the following four properties. It has digital inputs, it has digital outputs, it has a functional specification. And remember that the key characteristic of a combinational device is that it has no memory. That is, each of these outputs of the combinational device is a function exclusively of a combination of the inputs. Right? It's a function of the inputs only. And so that function needs to be precisely specified, and we'll see how to do that today. And finally, a timing specification that specifies at a minimum some upper bound on the time from the instant at which we get valid and stable digital inputs to the time at which the circuit will produce a stable and valid digital output. Okay, so we call the combination of these four things the static discipline. And last lecture we ended up with sort of the motivation for combinational logic, a key property of combinational devices is that they're very easy to compose. And we ended up with this list of sufficient conditions. So if you have a network of combinational devices connected with wires, as long as every input is connected to exactly one output, essentially something that provides a single digital value as an input, and then the circuit has no directed cycles, then we have the combination or the composition of these multiple combinational devices is also combinational. Now, the first property, or this property that each input is connected to exactly one output, is more or less obvious, right? You don't want multiple outputs to fight over setting a particular input. The one that was less obvious was this property that the circuit contains no directed cycles, and we call this having an acyclic network. And so we ended up with this example, right? And so the key problem with cycles is that you can have feedback loops that essentially cause the output to never settle to a valid digital value or maybe a known digital value. And so this very simple combination of two combinational devices, this AND gate that outputs a high voltage when both of its inputs are high, and an inverter, which we both saw in the previous lecture, will essentially, if you take the input from 0 to a 1, will oscillate, right? Will cause the output to oscillate. And in fact, here I'm drawing this nice square wave, but really we don't actually have the tools to know what the shape of that wave is. You have to go fairly deeply into the implementation of that AND gate and that inverter to figure out, does the output actually reach a valid digital value? Maybe if these gates are both very fast, then the output or this input starts going down very shortly after this output starts going up, and so this actually never reaches a valid digital value. So beyond the specific details here, these circuits are very hard to analyze, and that's why we're going to be essentially disallowing cycles to compose digital devices. So remember this, because lack of cycles is going to be a theme throughout most of the digital design, and so we'll eventually have to have cycles, but very carefully engineered cycles to have memory. So we'll get to that in 3 or 4 lectures. Okay, so the key focus of today's lecture is functional specifications. And so, I mentioned that the output is a function of the inputs. Well, how do we describe that function? Well, you can play word games, right? You can describe anything with words. And so, for example, in this particular circuit, you see that there are 3 inputs and 1 output, and a description that says, well, if C is 0, then copy A to Y, otherwise copy B to Y. Well, this works for very simple circuits, but it's hard to parse. Sometimes it's ambiguous. So we'd like to use systematic representations, right? Formal ways to specify the function of a circuit. And we will use 2 different approaches. First, what we call truth tables, which are essentially a table that enumerates the value of the output of each of the outputs for all possible combinations of the input. So in this example, we have 3 inputs that are either 0 or 1. So our truth table is going to have 2 to the power of 3 or 8 entries, right? And so you enumerate all possible input values. And then you can go row by row, essentially deriving the value of y. And so from this text description here, well, if C is 0 and B is 0 and A is 0, well, if C is 0, we copy A to Y, and so A should be 0. A is copied to Y, and so Y should be 0. In this case, A is 1 and C is 0, and so Y is 1, and so on. And so we could go and fill the table, right? So the first 4 entries are going to mirror the entries of A, and the last 4 entries are going to mirror the entries of B, right? Because we're copying either A or B. So truth tables are one approach, but there's another more interesting approach, because it lets us manipulate the function and simplify the function more effectively, that we call Boolean expressions. And these are equations containing binary values, so values that can have values that can be 0 or 1, so 0 or 1 constants, and then variables that can be 0 or 1 as well, and 3 operations, and, or, and, not. Now, in this lecture, and almost for this lecture only, we're going to represent and as a product, or as a sum, or as a plus, and then not as an overbar. But there are many different representations of these operators. So, and you will see, so here we're representing as a product. Some people represent it with X. You can represent it like this, or just like an and, or even 2 ands, right? Or we're going to use plus, but these other representations are also possible, and then not. We're going to use an overbar, so not A is A bar, but you also have not A and not A. And so you might have seen already all these representations in different programming languages. C, for example, uses these ones. Okay, so this is the Boolean formula for this particular circuit. So if not C, then copy A. And we don't need to go too much into the details of this particular formula. We'll see exactly how to derive it later, and in fact how to derive optimal or formulas that have the minimum number of operations. But the key concept that we're going to see, and one of the key results that we're going to reach, is that both of these representations are equivalent and they're complete. So any combinational device and the function of any combinational device can be specified as a truth table or a Boolean expression, either or. So the truth table is obvious, right? You just list the output value for all the inputs. The Boolean expression is less obvious, and we'll see the mapping in a few slides. Before we jump into these Boolean expressions, I'd like to spend a couple of minutes talking about time, which is the other important part of combinational logic. So we mentioned, or we said that one of the key properties of combinational logic is that you want the output to be ready in some bounded amount of time. right? And this is what we call the propagation delay. So precisely the propagation delay, which we denote with this TPD over here, is an upper bound on the delay from having valid inputs, valid and stable inputs, to having valid and stable outputs. So if you have something like an inverter, right, you can feed it a pulse with a rising signal, a rising voltage, and then a falling voltage transition in the input, right? And so what you'll see is, this depends on the particular implementation of your inverter or your particular combinational device, is that there will be some time during which the output does not change, and eventually it starts falling or it starts changing. And after some time, it reaches VOL, right? The output level that we said was representative of a valid digital output, right? So looking at this diagram, we can look at the delay from the time at which the input reaches a valid digital value to the output reaching a valid digital value, and we'll see that we have two transitions, so we have two intervals there. Both of these intervals have to be at most the propagation delay, right? So we're interested in the longest of all these, or the largest of all these delays. So our goal in circuit design is going to be to minimize this propagation delay. And you might be wondering, well, why do we care about the propagation delay being the worst case, right? I mean, if I have a circuit, it'd be nice if I could get, or we could care about the average delay or the minimum delay. So why is the worst case delay the thing that determines the performance of the circuit? Well, so this is not going to be obvious for a while, but this requires going a few topics ahead into sequential logic. And at a very high level, when you buy a processor, you might have seen that it has, or you buy a laptop with a particular processor, it's advertised with some frequency, right? Like this processor runs at 4 gigahertz. So what that number is telling you is precisely how many times per second we're feeding inputs to the combinational logic within that CPU. So what happens is, if we have a combinational device, right? So let's say we take some combinational device within the CPU. The way it's going to work is through what we call synchronous sequential logic. And so we're going to sandwich this combinational device. It's going to have multiple inputs, it's going to have multiple outputs. And so if we have what we call a clock frequency of, let's say, 1 gigahertz, that translates to a clock period of 1 nanosecond. So this is 1 over the frequency. And what this means is that every nanosecond we're going to give this combinational logic block new inputs and then record its outputs. The next nanosecond we'll go give it new inputs, record its outputs. And therefore we want the delay from any input to any output under all circumstances to be within 1 nanosecond, because otherwise we're not going to sample, we're not going to record the right value. So that is why we care about the worst case delay. And so we'll always be talking about the critical path delay, propagation delay, and so on. Okay, any questions? So there is another quantity that we'll see later, and we'll pay some attention to later, that is called the contamination delay. And this is actually sort of the dual of the propagation delay. It's a lower bound on the delay from the inputs going from valid to invalid to the outputs going from valid to invalid. So see here that when the input goes invalid, there's some time that elapses before the output starts switching. So that's the minimum of all those delays is the contamination delay. And we care about the contamination delay for reasons that will become very obvious when we look at sequential logic. That for these combinational devices to work with the devices that sample them, which we call registers, they actually need to stay stable for a little bit. So putting it all together, the entire combinational contract is, you have some combinational device, some functional specification, and some timing specification that depends on the propagation delay and the contamination delay. Given this, and given that we have digital outputs, we typically do this essentially represent the input and output waveforms using the simplified values where we have a digital 0, a digital 1, and then what's going to happen, so if we feed these values at the input, is that at the output we're going to get, for some time, the value is not going to change, and then after some time the value is going to reach a stable digital value, and then there's going to be this region in the middle where actually we make no promises. The implementation can do anything it wants, right? I've shown this nice exponential waveform in the previous slide, but during this transient we could have different transitions in the middle. So there are absolutely no promises. But if we measure the time at all the transitions from the time at which the input switches and reaches a valid digital value until the output reaches a valid and stable digital value, that must be what? That must be at most, that delay must be at most the propagation delay. And then these other intervals must be smaller, right? The interval from the input switching to the output becoming invalid must be at least the the contamination delay, right? Okay. Any questions? Good. So let's jump into Boolean algebra. Essentially, the way that we can interpret and manipulate Boolean expressions, which, remember, is the primary way that we're going to express the functionality of these combinational devices. So there are many, many ways of specifying or defining Boolean algebra. We're going to see a couple. Essentially, Boolean algebra comprises two elements. So you have binary values, 0 and 1. You can have true or false. And then these and, or, and not operators at the very least, right? So one fairly straightforward way of specifying Boolean algebra is by just giving the truth tables of the operators, right? So and, this is the truth table for and, so if A and B are listed here, A and B is 0 except when both A and B are 1. A or B is 0 only when A and B are 0 and is 1 if either A or B is 1. And then not A is 1 when A is 0 and 0 when A is 1, right? And if you just specify these operators and define these operators, all the properties that we're going to see basically fall out of this definition. So we're going to see a bunch of different formulas and a bunch of different ways of simplify Boolean and manipulate Boolean expressions. All of them can be derived from these three operators. However, if you ask mathematicians, they don't like truth tables. They actually prefer to express or formally define Boolean algebra using axioms. And so instead of having these truth tables, basically there are these three axioms that say there is an identity element for both and or. So essentially 1 is the identity element of and or is the identity, and 0 is the identity for or. So oring anything with 0 returns the same value, and anything with 1 returns the same value. There is a null element for both and or. So 0 is the null element for and 1 is the null element for or. And then negation is essentially defining not, right? And there is one very interesting property that you can start seeing here that is not at all apparent from the truth tables. So if you look at the set of 3 formulas in the left and the set of 3 formulas in the right, you see that they're very symmetric, right? In fact, if you switch all the zeros with ones in the formulas in the left, right, and you switch all the ands with ors, right, the formulas in the left transform into the formulas in the right, and the formulas in the right transform into the formulas from the left. And so this symmetry is essentially what we call the duality principle. So replacing zeros with ones and ands with ors, if a Boolean expression is true, yields another Boolean expression that is true. Now, a very interesting property is that because this holds for the axioms, and we derive everything else from the axioms, or all other Boolean algebra equations fall out from the axioms, then the fact that this principle holds for the axioms means that it holds for all expressions. And this is good, just in terms of practical purposes, apart from, sure, mathematically it's very nice. But it halves the number of expressions that you ever have to learn, which, if you ask me, that's nice. I only learn the left side, and then I can get the right side. So there are a few expressions that are very useful, or expressions or properties, essentially different equalities, that are very useful to learn because they help you manipulate expressions quickly. So when you're simplifying Boolean expressions, you'll basically want to memorize at least half of this table. And the good news is that a lot of these properties are very straightforward, and they are very much the same as you have in integer algebra. For example, commutativity, right? So A and B yields the same result as B and A, right? Same for OR. Also associativity, you can reassociate terms in operations involving multiple operands and sequences of the same operation being applied in any way you want. And so this associativity is actually very, very helpful to take a sequence or a chain of operations and turn it into a tree, which we will see is much easier, or it's much faster to implement in combinational logic. But be careful, because not all the properties are quite the same. So for example, the distributive property, this formula over here for AND should be very familiar, right? The same way that product, that multiplication is distributed over addition in integer algebra, AND is distributed over OR. But because of duality, OR is also distributed over AND, which is something that, plus is not, or addition is not distributed over multiplication in integer algebra. So there are some differences. And then, so these are sort of the 3 basic properties, and you have these other properties in the bottom that are very helpful to simplify expressions. So for example, complements, A and not A is 0, A or not A is always 1, absorption, reduction, and so on, and the Morgan's laws. So, my recommendation is that to learn these expressions, you just go ahead and prove them. And proving things is a big word, but with Boolean algebra, I promise that proving things is really, really simple. You can prove things just by using the different properties, and so just with algebraic manipulation. And so for example, let's prove reduction, right? So we want to prove that A and B, or A and not B is A. How do we go about this? Well, so we can say that thanks to the distributed property, right, this is equal to A and B and not B, right? And then, what is this? What property can we use from the ones here to further simplify this into A? So by complements, right, this is A and 1 And what is A and 1? The null axiom tells us it's A. No truth tables involved, I'm just using the different properties here, right?
It's not null, it's identity.
Sorry, identity. Okay, thanks. But you don't need to do this with algebraic manipulation. Let's take a look at trying to prove something just by doing the truth table. So one very useful rule, or one very useful equality, is the Morgan's law, which basically says that not A and B is equal to not A or not B. Essentially, you can push the bubbles down the operation, and that flips the AND to an OR, and the OR to an AND. So you can just do this by, for all combinations of values A and B, seeing where the values match, right? So if for A and B equals being, it being in this truth table, A and B is 0, 0, 0, 1, so not A and B is 1, 1, 1, 0. What is not A or not B? Well, so if A is 0, not A is 1, so these two are 1. And then if B, so if A is 1, B is 0, but in this case, if A is 1, not A is 0, right? So these two terms equal not B, and so we have 1 and 0, right? And so you can see that indeed they match. So we've proven that the Morgan's law, at least for AND, holds, and by duality it holds, the other one also holds. But you don't have to take my word for it, you can just try it out. Okay, any questions? Yes?
Is there a specific order of operations, or is it like, is there a specific order of operations?
A specific order. So what do you mean?
When you see, like in algebra, you do multiplication and then addition. Is it like you do and then or?
Yes. So the same rule applies. So if you see this formula over here, and has higher priority than or. So it's the same priority rule as the same precedence rules as within zero algebra. That's a good question, because this is going to arise multiple times. These kind of expressions are called sums of products, and you need to know that the products come before the sums, or the ands come before the ors. Okay, any other questions? Good. All right, so now I mentioned that the truth tables and the Boolean equations or Boolean expressions are equivalent ways of defining the functionality of a circuit. So let's see why that is. The reason why that is that if I give you a truth table, you can just derive a Boolean expression by going row by row in this truth table, and for all the ones, essentially writing what we call a product term, but essentially a term of input, a combination of input values that covers a single one in the truth table. And so this is the equivalent expression for this output here. Let's see why that is. So we want each of these terms to cover a single row of the output, right? And so to do that, this is going to be a product of, or an AND of all the values, or of all the input values, or their complements, right, or their negated values. So in this case, if we want to write something that's 1 only when C is 0, B is 0, and A is 1, well, that's not C, not B, A, right? Or not C and not B and not A, right? And so this term maps to this row, this term maps to this row over here, this third term maps to this row, and this term maps to this row. Now, you have a systematic way to take a truth table and turn it into a Boolean expression. This, in fact, is called the function's normal form, or more precisely, the conjunctive normal form, or CNF. There's a different disjunctive normal form that we're not going to use in this course. So this is also what we call a sum of products expression, right? Because you have a bunch of product terms, and then they're ORed. They're all added up. This normal form is unique, but it's not the simplest thing you can do generally. So in general, we're going to see that there are ways to write expressions that are simpler, and simpler expressions are good because they result in simpler circuits. But the corollary here is that given a truth table, you can always derive a Boolean expression for it. Given a Boolean expression, you can derive the normal form by turning it into a sum of products and then write the truth table, and so they're equivalent. Okay, so let's switch gears and move on into logic synthesis. That is, how do we take Boolean expressions and turn them into circuits? Yes?
On the slide, two before this, on the truth table slide, why is it that the relationships between C, D, and A is like as described by the table?
So why is this product representative of this row, for example?
Yeah.
So if you want a Boolean expression that is only 1 when a particular row of the truth table is 1, you can just write out an AND of all the input variables with a NOT over each variable where you have a 0, and just the variable itself without negation where the variable is a 1. Right? So you can see that the truth table for this term over here, right, is all zeros except a 1 here.
But a more basic question, if we're just dealing with one row, so like where C is false, B is false, and A is true, so that Y, or the result, ends up being true, why is that the case?
Why does the result end up being true?
Why is the result that Y is true when C and D are false and A is true?
Well, you have a term here that says it's the AND of 3 different variables, right? And so you're ANDing not C and not B, which are both 1, and then ANDing them with A, which is also 1. So 1 and 1 and 1 is 1, and so you have a 1 there, and 0 elsewhere, because no other combination of inputs will cause that product term to become a 1. Now, that's why when you're ORing all these different product terms, each of which refers to one particular row of the output, you end up with the combination of values of 1 values that you want in the output, right? The exact combination that you want. Does that make sense?
No, but I'll ask it.
Okay, so we can take it offline. Okay, so as I mentioned, we want to go from Boolean algebra to circuits. And to do that, we're going to first use logic diagrams, which are just a representation of Boolean expressions using a circuit schematic, right? Just a diagram connecting logic gates or basic combinational circuits with wires. And so we call them gates and not basic combinational circuits, but they're just that, right? There are some base elements that we're going to build much more complex circuits out of. The most basic logic gates are essentially AND, OR, and inverters. And inverter, the AND gate and the inverter we've already seen. So AND performs an AND operation, right? So given digital inputs A and B, it's going to output A and B at the output. ORs, an OR gate, you see that it's similar to an AND gate, except you have this wobbly thing over here. That's the key difference. And so that outputs A or B. And then the inverter is this triangle, and it is quite important to see that there's a bubble at the output of that triangle. So that is, in fact, what you'll see in many circuit diagrams is that people just don't draw the triangles, and they just draw bubbles. And every time you see a bubble, that means you're inverting the signal. Now, these are 2 input gates, but we often use gates with more than 2 inputs. So here's an AND gate with 4 inputs that outputs 1 only when A and B and C and D are all 1. And then, one interesting property is that AND, OR, and NOT are universal. They can implement any combinational circuit. Now, why that is the case goes into the equivalence between between truth tables and Boolean expressions. So let's see it in more detail, right? We can just see this by constructing a way to turn any Boolean expression into a circuit that has AND, OR, and NOT gates, right? Let's go ahead. And this is basically, if we take the normal form, or in any other instance what we call a sum of product terms, right? A sum of products expression. So any expression that is the OR of a bunch of terms that are ANDs of different input variables. You can just express anything of this form, any sum of products Boolean expression, with 3 levels of logic, right? The first level is just a bunch of inverters where you're generating the negated values for the signals, where you need both the signal, the input itself, and its complement. So here we need both C and not C, and also we need B and not B. And in fact, in this case, we also need A and not A. And so you can see that there are some gates here that are generating the complements. Followed by a bunch of AND gates, each of which implements one of these particular product terms, right? So this AND gate, or the combination of this AND gate and the 2 inverters at its inputs, is A and not B and not C, right? Followed by an OR gate that adds up all the outputs of these AND gates, right? And so this circuit implements this particular function over here, right? Any questions? So now you can take any truth table or Boolean expression and write or draw the circuit for it, right? And you could go buy AND gates and OR gates and implement it and have your logic circuit. Now, that's nice, but this implementation is unfortunately not very good. And the reason is that this Boolean expression itself is more complex than it needs to be. You start looking at it, you'll see that there are ways that it can be simplified. And so here's where we're going to link both. Basically, you see that each of these ANDs, right, turns into either an AND gate or an AND gate with more inputs. AND gates with more inputs are more expensive. And then each of these terms, or each of these OR operations, affects either the OR gate or the number of ORs that we're doing. So we want to, in general, simplify these expressions to reduce the number of operations that we're doing, and therefore the number and the complexity of the gates that we're using. So we can do this by essentially using the properties that we've seen before to manipulate expressions, right? And to essentially achieve what we call a minimal sum of products. So a minimal sum of products is just a Boolean expression in sum of products form, right? In the same form that we've seen before, that has the smallest number of and OR operations. And in this case, NOT operations are free. We'll see why they're free when we start looking at the implementation of these gates. These gates are generally, in current technology at least, they're inverting. So there can be multiple solutions for a minimal sum of products expression. So you can arrive to different answers. And the way to do this is essentially with simple algebraic manipulation. So just as an example, let's take the expression that we had before and try to simplify it. And you can take a look at the different terms and say, well, the 2 terms in the middle here are actually, I could reassociate terms, and it's CB, C and B, right? And then parentheses, not A or A, right? And so by reduction, that can be simplified. These 2 terms can be simplified to just C and B. And again, by applying reduction, these 2 terms can be simplified to not C and A. And so we end up with this much simpler expression, that is doing just 2 ANDs and 1 OR, right? And the implementation of that expression is going to be much, much simpler. Okay, there are more sophisticated techniques. So at some point in 004, we spent quite a bit of time talking about Carnot maps, which are a graphical technique to derive simpler expressions. And you're welcome to learn them on your own, but we're not going to require them here. We're just going to stick to algebraic manipulation for simplification. And the contract here is that the expressions that we're going to give you are always going to be able to be simplified into a minimal sum of products just by repeatedly applying the formulas that we've seen, right? The properties that we've seen. So, there are other optimization techniques that are more complex. We're not going to see them here, and we'll see why not in a couple of slides. There's another technique that you'll see in recitation, and the basic problem here is that for very small circuits, this sort of sum of products expression works. But in general, we're going to be designing combinational circuits that use multiple levels, right? That rather than having just 3 levels of inverters and OR gates, they're going to use more. They're going to be deeper circuits. So just to give you a flavor of how deep, in modern processors, you have anywhere between 8 and 24 AND gates worth of depth in a single combinational circuit. And when you can have multiple levels, there's a whole slew of techniques that you can start using to simplify circuits further. So, for example, if I give you this Boolean expression f, this is a minimal sum of products expression for it. It's A and C, or B and C, or A and D, or B and D, right? But you can start reassociating terms and turn these into A or B and C, or A or B and D. And then you can do what we call common sub-expression elimination, right? So figure out that A and B is computed twice here, and so we can just reassociate terms and compute X before, and then have F being computed as X and C, or X and D. And if you do that, you end up with this circuit, right? Where you first have an OR gate to compute X, and then 2 AND gates to compute these 2 product terms, and then an OR gate. Now, this circuit has 4 gates. This circuit over here would have many more gates, right? 1, 2, 3, 4, and 2 input AND gates, and either 1 4-input OR gate, or at least 3 2-input OR gates. So we've gone to a much simpler design. However, these designs might have more delay because there are more levels here. So the key takeaway here is that once you start adding levels, there's no well-defined optimum. Sometimes you end up with hard area versus delay trade-offs, right? You're going to have something that is going to take a lot of area, or that is going to give you a lot of very low delay, but it's going to have a large amount of area, lots of gates being used for it, or fewer gates but more delay. So in practice, we're not going to do this full-blown optimization manually because it is a really, really hard optimization problem. And so in practice, we're going to use synthesis tools. Synthesis tools essentially take 3 inputs. So you start with some high-level circuit specification. For example, we can have the Boolean expression for the combinational circuit that we want to implement. We can describe them in minispec, which is what we'll be doing in the labs from now on. And we also need a standard cell library, essentially a library or a set of gates and their characteristics. How much delay area do each of these gates consume? And some optimization goal. Do you want to minimize delay? Do you want to minimize area? Do you want to minimize power? Do you want some product of targets? And so on. And so in the end, these tools will give us some optimized circuit implementation according to applying a bunch of Boolean simplification, but also many other techniques to try to derive efficient circuits. Let me spend a couple of minutes talking about the standard cell library, which is something that you're going to see for the first time in Lab 3. So we've talked about AND gates and OR gates, but there are some or a few other common gates. There's first of all what we call XOR. So here's the truth table for XOR, and an XOR is almost like an OR, except there's this double line here. That's how you can distinguish them. The expressions involving XOR, XOR typically has this operator, this plus with a circle around it, and basically given A and B, the output of an XOR is 1 if either B or A are 1, but 0 if either both are 0, both inputs are 0, or both inputs are 1. Can you tell me the Boolean expression for this? Yes.
A not B plus B not A.
Perfect. Yes. Just look at the truth table. And you can directly derive the Boolean expression, right? Also, we have inverting logic, inverting variants of AND and OR gates, and these we call NAND and NOR, for negating AND and negating NOR. So these return not A and B, and not A or B. And the difference between AND and OR is, again, that you see these bubbles at the output. Right, so that's telling you that these are inverting. Now, one cute property of NAND and NOR is that they're universal. So a universal set of gates, or we say that a set of gates is universal if you can build any circuit with them. So before we said AND, OR, and NOT are universal, sure. But let's just take a look at NAND, right? Well, if you type up both inputs of an AND gate, you end up with an inverter. If you follow that up if you follow an AND gate with this inverter, then you end up with an AND gate. And then by the Morgan's law, you can get an OR from an AND, right? And so, again, you can derive an OR gate. And because you can get all three operations, just an AND gate is universal. It's a very useful property if you only have NAND gates and you just want to build your entire circuit out of one type of gate. Some technologies have done this in the past. Today, we have a few more types of gates. So, in fact, if you look at a standard cell library, if you want to build your circuit, you'll go to some circuit manufacturer, for example, TSMC, and they'll tell you, look, here's the list of different gates that we have, and here are their characteristics. And so this is just one very simplified example where you have things like inverters and buffers, and each of them takes a certain area in your chip, has a certain amount of propagation delay. Right? There are 2 input AND and OR gates, NAND and NOR gates, and then 4 input AND, NAND, or NOR gates. One observation here, and this we'll see in much more detail when we learn about CMOS, the technology that is used to build these underlying gates, is that first of all, inverting gates are faster. So are faster and smaller. So you can see, for example, that this NAND2 gate takes 30 picoseconds and takes 15 square microns, whereas an AND2 gate takes 50 picoseconds and 25 square microns. And so generally, you'll see good implementations using inverting logic, NANDs and NORs, rather than ANDs and ORs. So given this, well, and the other detail here is that gates with more inputs take both more area, and that we'll see is because they use more transistors, and also, take more area and then also have more delay. And we'll see exactly why that is in a couple of lectures. So given this, you can actually take a function like AND4 and look at different ways of implementing it. Right? So for example, you can just use the AND4 gate, which will give you a propagation delay of 90 picoseconds and 40 square microns. You can use an AND4 gate followed by an inverter, which curiously has the same propagation delay and the same total size. And you can start guessing that in fact the AND gate is just an AND gate followed by an inverter. There's not much magic there. But there are more interesting combinations of gates that actually give you AND4, right? So 2 NANDs followed by an OR. This also gives you a a 4-input AND gate, or is equivalent to a 4-input AND gate, and this is because of the Morgan's law. This is equivalent to an AND gate with its 2 inputs negated, and so these bubbles essentially cancel, and you end up with AND. Now, if you look at the propagation delay, that's 1 AND and an OR, and so that's 65 picoseconds. So that's actually faster than a single 4-input AND gate. The size, however, is the size of these 2 NAND 2 gates and an OR gate, and so that's slightly larger, right? So you're going to end up with these delay area trade-offs all over the place. And so then you can start, taking a standard cell library with different amounts of area and different amounts of delay. You can get a circuit, or a Boolean expression that represents a circuit like this, and map it in different ways using different combinations of input gates. This, for example, has 32 area units. This other implementation here, which uses NAND 3 and NAND 4s instead of only NAND 2s, has 19 area units. Now, you're not going to do this manually, and this is the final point that I want to make in this lecture, that this is a very hard optimization problem. We don't want to bore you with all the logic optimization tooling and so on, and doing this manually is just extremely tedious. And so what we're going to do is use synthesis tools to do this automatically for you. But what you need to do, and what you need to know, is how to minimize and to apply Boolean simplification to essentially turn any Boolean expression into a minimal sum of products, because that is a useful skill. All right, so that's all for today. Thank you. Next time we'll actually start describing much more interesting and complex combinational devices like adders and comparators.